Which of the following are aromatic? So aromatic compounds are compounds that are particularly stable. They have a larger delocalization energy than can be explained by just simple resonance. So it's nice if we can recognize when a molecule is going to have this property. So the most common example of an aromatic compound that you're going to see is benzene. So this is the first one you're introduced to. And so here's the structure of benzene, and we want to take a look at applying the criteria for aromaticity, and we'll use benzene as an example at first. So what you need to have is an uninterrupted cyclic pi electron cloud. So this allows for you to have resonance completely around that cyclic system. So in order to have that, the following criteria must be true. The molecule must be cyclic. It must be planar. So it must be flat so that those p orbitals can effectively overlap above and below the plane of the ring. And so to make all that happen, that also means that every atom in the ring should be sp2 hybridized. That would allow us to have p orbitals or pi electrons on each of those atoms. And it would also make this planar since we know that sp2 hybridization is associated with trigonal planar. And then furthermore, once we've established that it's cyclic and planar and everything is sp2 hybridized, your pi electron cloud has to contain a certain number of pi electrons. And that number is easiest described by counting in electron pairs, and you're looking for an odd number of electron pairs. And that will be the fastest way to count it. So if we take a look at benzene, we can see that it is definitely cyclic. We know that it's planar because every atom in this ring is sp2 hybridized. And for an odd number of electron pairs, so we're counting just pi electrons. So whenever you have a multiple bond, one bond is sigma and one bond is pi. So for each of these, we can count 1, 2, 3. So this has 3 pairs of pi electrons. Okay, so benzene is easy to recognize. What we want to do is be able to apply this criteria for aromaticity to compounds besides benzene. So if we take a look at the first example, I think these sort of structures are the easiest to recognize. The way that I describe this is if you see a molecule that looks like you've got a bunch of benzene rings stuck together, then it's aromatic. But we can go ahead and apply this criteria to see how it's aromatic all the way around that outside cycle. So every single atom of these rings is sp2 hybridized. It is planar. It's definitely 2 ring systems. And then if we count our number of electron pairs, we have 1, 2, 3, 4, 5. So this compound is aromatic. If we move on to the second example, okay, it is possible to count electrons that are lone pairs of electrons as pi electrons if they can be delocalized. And we can draw resonance, right? So we can count one of those pairs of pi electrons as part of our pi electron cloud, but what we should notice before we get to counting those electron pairs is that we've got an atom here that is sp3 hybridized. So that makes it so that even though you have delocalization on this part of the ring, it's not around the full ring, so this one is not aromatic, okay? If we move on to this third example, we again have a lone pair of electrons, and so this nitrogen could be either sp2 or sp3 hybridized. If you had no resonance, it would be sp3, but if you are able to draw these lone pairs into resonance, then that means that that nitrogen is sp2 hybridized, and we can count that pair. So we can count that lone pair, and this one, so it does have that odd number of electron pairs, and so this is aromatic. And so then if we look at 4, this is actually very similar to what we just looked at in 3. It's just that our lone pair is an anion on carbon, but we can draw the same sort of resonance, which means that we can count that pair of electrons as being pi electrons in a p orbital. And so we again have 3 electron pairs, and so this one is also aromatic. So if we look at our options, then we can see that it is 2, 3, and 4 that are aromatic. This is a good example of how we can have larger ring systems that are aromatic and how we can treat lone pairs of electrons.